Je pense que Amie va maintenant parler.
Go ahead.
Okay. So it's a pleasure to participate in Christian's birthday and celebrate his love for mathematics. And also to present Amie Wilkinson from Chicago, who will speak about asymmetrical diffeomorphisms and the C1 topology.
Okay, while I'm trying to find my talk, I would like to thank the organizer, for putting this together. We're all sad that we can't see each other in person, but this is pretty great. So Lorenzo and the organization, just glasses up to you, a little round of applause. Okay. So I would like to see as many of you as possible. I have 2 screens. I know that that's asking a lot since I tend to hide myself when I give a talk, but I can see every one of you because my talk is on a different screen, is on my iPad. So I can tell if you're lost or whatever. So I'm going to talk about a collaboration with Christian that happened more than 10 years ago with Sylvain and Joya as well. I think she's here. It's something that there's been some recent related work.
Sorry, can I ask something?
Yeah.
So you prefer for us to leave the camera on?
Yeah. But you don't have to. It's okay if you need to go do something else. But yeah, I'm looking at all of you, which makes this a little less weird for me. All right. So I first met Christian in, everyone make sure you mute because I'm hearing echoes of myself. Okay. So Christian and I first met, I believe, in La Bussière in 1999. I was 8 months pregnant, and I don't remember much other than being very pregnant at a conference in Burgundy. And I can't find any pictures. But the next time we met, and I remember this a little better, was at IMPA in August of 2000, and this was the 60th birthday conference of Jaco. And here's the conference picture. I can't find any other pictures from this conference. After looking a long time, I found myself. I still really can't find Christian in this picture. But I do remember the first time I saw Christian at this conference. Lizzie Burslem and I had just arrived at our hotel, had no idea where to go, ripped a page out of a phone book with a map and found our way up to IMPA. And I saw Christian, one of the first people I saw, and he complimented my pants. Anyway, that was a fun conference. And then probably where I got to know Christian much better was a year later in Evanston at a conference that Keith Burns and I organized on partial hyperbolicity. And there on the left is Lizzie Burslem, right there. And I suppose you probably know who that is. And I'm not, and that's Marcelo, and I'm not sure who that is, but anyway. So, okay. So this talk concerns the interplay between the algebraic and dynamical properties of the group of diffeomorphisms of a closed manifold. So throughout the talk, I will fix M to be a closed manifold and denote by diff R of M, the set of CR diffeomorphisms of M endowed with the CR topology. So diff RM is a topological group. Composition and inversion are continuous in this topology. Kind of a cute fact, the algebraic properties of the group completely capture the smooth properties, the topological and smooth properties of M. So this was proved by Filipkowitz in 1982. If you have an isomorphism between a CR diffeomorphism group and a CS diffeomorphism group of potentially another manifold, then the R is equal to S, and the two manifolds the isomorphism is induced by diffeomorphism. So this group, the algebraic structure of the group, captures a lot of the properties, the smooth structure of M. So some questions from classical dynamics. Fix an element of the diffeomorphism group and iterate that single element. You know, what long-term behaviors do you see in M? For example, periodic points, recurrence, dense orbits, positive entropy, chaos, and so on. So I'm going to assume we're all familiar with these types of questions. Modern dynamics, I could put this in quotes perhaps, would be to consider subgroups of this group of diffeomorphisms. So a single diffeomorphism generates a Z subgroup. But now consider larger subgroups. There's been quite a bit of recent, very interesting work on this type of question. But just the sort of general questions, you know, which subgroups can occur, you know, if they do occur, like if you put some assumption algebraic on a subgroup, does it restrict the dynamics of the elements of that group? You have a notion of iteration in a, let's say we're talking about finitely generated infinite groups. You can talk about things like orbits by, you know, how far away you are from the identity in the group in some word metric. So I want to talk about some interplay between the two in the case of a C1 topology. Surrounding classical dynamical questions, there are genericity questions. So which of these properties are, you know, a sort of generic question one might ask is which of these properties are generic or hold generically in certain parts of the space of CR diffeomorphisms of M. But I want to focus on questions you can ask about the generic diffeomorphism with no other assumption. So one would imagine that you can't say very much about the generic diffeomorphism or, you know, much about its dynamics because it's such a general question. So, well, one example is the Kupka-Smale theorem, which says that for any R, if you take a CR generic diffeomorphism, that means F belonging to a residual subset in the CR topology, then for every K, the number of fixed points of F to the K is finite. And moreover, those fixed points are hyperbolic, and moreover, the intersection between stable and unstable manifolds is transverse. So this is atypical in a couple ways. So the first way, sort of atypical thing about this result is that it applies to all diffeomorphisms. It's not a statement about the generic axiom A diffeomorphism or the generic Morse-Smale diffeomorphism or so on. It's the generic diffeomorphism. And the other atypical feature of it is that it's actually been proved for all R. Just a remark, if something is CR generic, it might not be CS generic because a generic property belongs to a countable intersection of open and dense sets. And if S is less than R, then it's harder to be open, but it's easier to be dense. So you can compare CR open properties with CS open, but not residual because it mixes the two. That's just a remark. So many genericity results have been established only for R equals 1, and Christian has played a big role in this. And I want to talk about some of these results, specifically related to the work that Christian Sylvain and I did a little more than 10 years ago. So why is it that for the grad students here, in particular maybe for the grad students from the University of Chicago who haven't seen very much of this, why is it true that we know things about C1 generic diffeomorphisms and not about C2 generic? Well, the reason is many sort of dynamical properties that stem from things like hyperbolicity are sort of easily seen to be C1 open. You know, there are certain things where you have to use finer C2 information to establish genericity properties, but C1 openness for a lot of the kind of questions that one's interested in is sort of relatively easy, just by the nature of the questions. And on the other hand, C1 density is always easier than C2 density. And that's because of the flexibility of the C1 topology that I'll sort of mention briefly in the next slide. And so, well, the famous example of something that's known C1 but not C2 is the closing lemma of Pugh, which states that if an orbit of a diffeomorphism or flow is recurrent, then it can be made periodic by an arbitrary C1 small perturbation. So given any point, if its orbit, oops, did you just lose? No, you didn't lose me, sorry. If its orbit accumulates on itself somewhere, then one can approximate that accumulation point by changing C1 small, you can make that orbit close up. All right. So another thing about Christian is he draws really good pictures, and I stole this picture from a photograph of Christian's blackboard. Okay, so this is or one of Christian's talks. So I want to illustrate why it's easier in a picture, why it's easier to C1 to C0 close something than to C1 close something. So here's an orbit of a flow. Maybe it's in 3 dimensions. You don't know. It's accumulating around here. It's accumulating on itself. And we want to make a small perturbation to close the orbit. And so to do this by C0 small perturbation, we focus on some place where there's some recurrence. And we find a particularly close return of 2 parts of the orbit. So, you know, it took a while for this point here or this kind of segment of the orbit to recur, but it did eventually. And now, if we just do a very small change, so what did I do here? I don't know if it's totally clear in this illustration. I kept this line the same, this piece of orbit the same, and then I moved this down here, and I kept this the same, and then I did whatever else I needed to close things up. And if you trace this picture around and cut out the extraneous matter outside the location of this perturbation, you see that we've closed this orbit. But this is not a C1 small perturbation because we've gone from, we had to keep this orbit and this orbit the same. Particularly, we had to keep this piece of orbit the same to make this perturbation work. And these 2 could be incredibly close because we actually looked for a close return in order to make this perturbation. And here the derivative has gone from 0 to, well, you know, it looks like -1 in a very tiny place. So it's not a C1 small perturbation. And if you tried to make a C1 small perturbation, what would that look like? It would look like sort of very gradually changing the slopes to kind of move them down. But you can't necessarily do that, right? By an arbitrarily small perturbation, if your scale gets small enough, such a perturbation like this does not actually close the orbit, for some examples. Okay. So what's the nature of Pugh's perturbation? Just a quick picture. You don't do a local perturbation as you would do in the C0 topology. You perturb along the orbit, and you see you make very, very small changes to the flow in this picture. There's nothing big close up, and in that way you're able to achieve this with a C1 small perturbation. If you haven't read his closing lemma, there's a really nice, for the students out there, there's a really nice paper, very short, by Clark Robinson that explains it very well. Now with a C2 small perturbation, except under some additional special assumptions, the question remains open. although it has been shown, you can sort of formulate this properly, that you know, there are examples where there's no, you can't localize a perturbation around an orbit in order to close it. So it requires a global perturbation to achieve this kind of closing. So it's a very different question, very different nature. Okay, so I mentioned that the C1 topology is more flexible. So what are the key features of the C1 topology? By the way, everything I know about the C1 topology, I learned from Christian Sylvain, basically. So, you know, I hope they jump in and interject if I say things that aren't quite right. Okay, but here's some key features. Well, the first, and we talk about this in our paper, is that on small scales, if you look very close to an orbit of a C1 diffeomorphism, it looks linear. Okay, and that's, well, simply, I mean, this is just the definition of differentiability. So in fact, if you're differentiable, you look linear on small scales, or affine if you like. And if you are C1, then that linearity is sort of uniform. You can sort of uniformly control, at least under finitely many iterates, how nonlinear something looks. And so what it means is that for all intents and purposes, you can almost think of a C1 diffeomorphism as being linear. And problems that you need to solve that concern perturbing orbits or perturbing close to an orbit on an orbit. Okay. And so there's been huge progress in understanding the properties, dynamical properties that are generic or open or dense in the C1 topology. And I'm just listing a few names here, and I'm leaving off a lot of names as well. And in fact, I would say kind of the person who, to my mind, has maybe the deepest vision about how one might go about classifying kind of C1 generic type of classification of C1 dynamics is in fact Christian himself. So I don't know if Christian, do you still, is this a picture you would still stand by in terms of kind of
So
how
I
you
still
see?
believe this picture.
You still believe this picture, and do you know when this picture was from?
Sorry?
When did you draw this picture? Do you remember?
I guess so it's some years after Beyond in China, because
Wow.
I thought on that because of Lan. We told me to do it more or less. It's Lan who asked me to do this kind of global picture.
I see. Cool. Yeah, I think Lan was certainly on my previous slide. So I just wanted to show this picture. I'm going to now go back to the question of quote unquote modern dynamics and how dynamics of iteration kind of interacts with some of these more algebraic questions about subgroups of diff. So what would be, in the context where we're interested in algebraic properties of diffeomorphisms, what would be a good sort of generic type of question to ask? Well, here's one. Suppose I choose a generic pair of diffeomorphisms. What group do they generate? I mean, they generate a group inside of diff. Is that group free? Well, the answer to that question is, in fact, yes. And this is not so hard to prove. I won't give the proof here, but there's a paper of Etienne Gis where he explains it for the circle. And it's a completely general argument. So if I take a generic tuple of diffeomorphisms, they in fact have no relations. But here's a question that seems similar, but is really not easy. So now pick a generic diffeomorphism. Does it commute with anything other than powers of itself? Okay, so does the generic F have trivial centralizer? So the centralizer that I denote ZR of F is just the set of diffeomorphisms that commute with F. And trivial centralizer, well, certainly the powers of F commute with F. Trivial centralizer means nothing else. So we can think of a centralizer. I mean, if FG equals GF, yeah, it's doing so well. Hold on. If FG equals GF, then GFG inverse equals F. So you can think of G as a map that conjugates F to itself. So it's a symmetry of the system F. It maps orbits of F to F. It preserves, you know, any sort of invariant of F. If it's a diffeomorphism, it preserves even smooth invariants of F. You would imagine that a system with symmetries other than those that you would just expect should be very rare. And that's what Smale asked. So he asked, is it true? And now the wording is a bit, it's not like he posed it in such a way very cleverly that you could have sort of interpreted it more than one way. But basically he asked, is the generic diffeomorphism have trivial centralizer? The answer on the circle is yes. So for R at least two, Nancy Coppell in her thesis in 1970 proved that for the CR generic diffeomorphism of the circle, the centralizer is trivial and for any R. So what did she use? Why R greater than or equal to 2? Well, she used a distortion in a key way. She used a control on distortion. Right, so we all know the kind of the distortion inequalities that you see in the circle, for example, when you study Danjois counterexamples. Okay, so she used a control on distortion and proved this. Now, there were subsequent partial results. I should maybe add Pallas as well, because he proved that the generic diffeomorphism does not embed in a flow. So that's a simple example. Right? If you embed in a flow, a smooth flow, then your centralizer is at least like R or some quotient of R. Anyway, but Palaciocos considered this question for Nossoff diffeomorphisms, axiom A diffeomorphisms. Lizzie Burslem, whose picture you saw at the beginning, considered the question for certain partially hyperbolic diffeomorphisms with one-dimensional center. And there's work of Todd Fisher, and there's work of others as well. So these were mostly for C2 or C infinity generic type of questions. So as I said, maybe 12 years ago, I don't actually know when the collaboration started. I think Christian did start when I visited Dijon, I think so, and Sylvain was a postdoc there. And yeah, is that right? Yeah. So that was, yeah, this is one of my favorite collaborations. I just can't let go of these guys. So we proved the actual full conjecture in the C1 topology. So using the flexibility of the C1 topology, and I'll try to give you a sense of why. So C1 generic diffeomorphism of any closed manifold has trivial centralizer. Or in other words, there's a residual subset. So that's a set that contains a countable intersection of open and dense sets. So that any F in the set has trivial centralizer inside of diff1. So I'd like to just give you a tiny bit of a sense of how, I'm not really keeping track of time, of how, kind of how this proof goes, and in the process, give you a picture that you can kind of glean out of the work of Christian Sylvain, which builds on the work of others, I should say, but it was a huge breakthrough. Okay, so how do we do kind of what's the easy case of this? Okay, so remember I told you, the easy case is like the circle, right? Well, I'll do it for the interval, right? So certainly for an open and dense set of diffeomorphisms of the circle, you have finitely many periodic points. So you can take like a power, and then you have these invariant intervals on which the dynamics is just North Pole, South Pole, so to speak, you know, attractor, repeller. So let's consider that case where we just have an interval and F has a unique fixed point inside of that interval, and it's a contraction, okay? And I'm going to be talking about the generic F, but for a second, let's just suppose we have F with this property, and now consider G some other diffeomorphism. So, and suppose that GF is equal to FG, okay? Then, oh, I knew this was going to happen. Okay, I'm going to try hard not to, because I'm trying to do this on a tablet. So GF equals FG implies that G F to the n, right, equals F to the n of G, composed with G. So let's just fix some point on the line. I don't know, let's just call it Y. And let's think about the, first of all, F to the n of Y is like somewhere over here, very, very close to this fixed point, which I'll just call X. Okay, so using the chain rule, I get the G prime at F to the n of X, or I'm sorry, of Y. Okay, F to the n of Y times F to the n prime of Y is equal to F to the n prime G of Y. Who knows where G of Y is? Somewhere else, maybe it's here. Times G prime at Y. Okay, and so then let's just write down what this implies. It implies that F to the n prime at Y divided by F to the n prime at G of Y, that's a prime there, is equal to G prime at F to the n of Y divided by G prime, G prime F to the n of Y, G prime Y, F to the n prime, G of F to the n prime of Y. So over here I should have G prime at Y, not F to the n of Y. Doesn't really matter, but so over here we got G prime of Y divided by G prime at F to the n of Y. Okay, now, a lot of people who are used to doing C2 distortion estimates think, well, in this case, we can conclude that the ratio of G prime of Y to G prime of F to the n of Y is bounded. But that doesn't give you any information. But we're not working with the C2 diffeomorphism. So this expression is bounded, right? I mean, it's just the ratio of the derivative of G at one point with the derivative of G at another point that's very close to X, yeah? So the key thing is the C1 generic diffeomorphism is not C2. And so the ratio of the derivative of F to the n prime at Y and F to the n prime of a different point, G of Y, is unbounded typically. And so you can state this as, and this is like an exercise, but the C1 generic F has the property as the following property. If I take the derivative of f to the n at y divided by the, and I just mean the one-dimensional derivative, so if the ratio is bounded for all n, then, well, there's only one way that this can be bounded for all n. I mean, there is one obvious way this can be bounded for all n, and that's namely if z is equal to f to the k of y for some, right? Because in that case, you know, by cancellation, I just get the kth derivative, and right? So generically, this is the only way that you can have that bounded property. So it's totally unbounded distortion. And so we conclude over here, if f is generic, then g of y is equal to f to the k of y. And it has the property, I should say, for all y and z. So generically, this statement holds for all y and z. And so then g of y is f to the k of y for all y. But then by the connectedness of the interval, that k is constant. So how would you prove such a thing? Just since I promised you some kind of understanding from the topology, some understanding that would come from the topology, C1 topology, let's suppose, I mean, it's a bare argument to get a generic thing, but imagine we have two sets, and these two sets have disjoint F orbits, and they're open. And I want to show that if I take any point in this set and any point in this set, then the derivative of f to the n of y and divided by the derivative of f to the n of z is unbounded. Okay, so I want to make a perturbation so that's true. Well, if those intervals are small enough, then f will just take this to pairs of intervals that continue to be disjoint. Okay, and well, I suppose it could happen that they're already unbounded, in which case you're sort of done, the ratios of the derivatives. But if not, if you just make a tiny little epsilon perturbation of the derivative along here in each step, then one of them, you can just cause exponential growth in the ratio. So I should say bounded above and below, I should say. Okay, and the reason you can make those little perturbations of the derivative in these tiny little scales is it's the C1 topology. So you're rescaling some tiny little change in the derivative. And then you use a bare argument to show, you know, you've done this for pairs of open sets with disjoint iterates, and then you can do it for every pair of points generically. So any questions? That's the easy case. Okay, so how do we go the easy case to the general case? Well, we need to understand what the C1 generic diffeomorphism looks like. And so I put together this little picture based on kind of the stuff we use in the paper. So here's our manifold M, here's our manifold M. Okay. And I'm going to show you what the generic diffeomorphism looks like. So I've drawn the periodic points. The bigger ones, they have higher period. There's finitely many because of Kupke-Smale. There's finitely many of a given period. So you can imagine as the periods get higher, you see more and more, but there's only finitely many of a given size. Okay, so those are the periodic points. And now let's look at the wandering set, the set of points that who have neighborhoods, wandering neighborhoods around them. So, well, some of these periodic points are going to be sources and sinks. And so their basins will be wandering. And then there'll be some like truly wandering, you know, so I should say the basins minus the periodic points. And then there'll be other, no doubt, other wandering components, because we're not assuming any recurrence. This is what makes it so hard to understand the sort of general diffeo. Okay, And then, so the complement of the wandering set is the non-wandering set, okay, which I've just drawn in orange. I appreciate all of you who are still here looking, I can look at. So what did Pew show? So Pew's closing lemma shows, with not much more work, that periodic points are dense in the non-wandering set. So obviously there's not going to be any periodic points in these blue regions, but these little dots are completely dense in the orange region. Okay, so that's C1 generic. Okay, so now let's look at the interior of the non-wandering set, because the non-wandering set is not necessarily open. In fact, it might be nowhere, dense, right? Okay, but anyway, let's look at the interior. So, and let's just pick one component of the interior. And now let's pick a point. I put it in green. So a point in some component of the interior. And here's what Bonnetti and Corvisier showed. Well, they showed a theorem basically that allows you to generically close chain recurrent points. But as a consequence, you get the following. The stable manifold of this periodic point is dense in that component. Okay, so that's the picture that we're going to use to prove that the C1 generic diffeomorphism is trivial centralizer. So, well, here's the big thing you have to believe, that the easy argument I gave you before allows you to show that for any periodic point, if I look at the stable manifold of that periodic point, so maybe the easiest case would be to consider first just a sink or a source. So I should say stable, yeah, stable manifolds dense. So maybe it's easiest to consider this case first. If I could show that for any 2 points in this stable manifold, the log of the Jacobian, sorry, of f to the n along the 2 orbits, the ratios are unbounded. So an unbounded distortion property similar to a contraction on the line, then I would know that inside, for example, of this right here, inside of this basin, F has trivial centralizer, my generic F. Do you agree? I do a little bit of a perturbation and then I can ensure this unbounded distortion. Okay, so I can do this to all, and I can do it for wandering points even easier because I just need to do perturbations down an orbit. And if the orbit ends up at a fixed point, or if the orbit just wanders off in perpetuity, it's very easy to make small perturbations and use a Baire argument. Well, similarly, I can take a periodic point inside the interior, a component of the interior, and now you have to believe, because it's a little bit less obvious, that you can do the same argument for pairs of points on the same stable manifold of a periodic point in the interior. Okay, and so you could get that, if you could do that, then you get that in each component of the wandering set and in each component of the interior, we have that generic, for the generic F, Fg equals Gf, and for any G, Fg equals Gf implies that F is some power of G. Well, what power it is could very well depend on the component. So just to remind you of our theorem, and so here's the outline of the proof. So the first I've already described. So we distinguish orbits from each other locally by perturbing derivative down the iterates and getting unbounded distortion in the ratio. I think it's just in the ratio of, yeah, you have to use a cocycle. No, I actually think we use the norm. So it's a little more tricky than using the Jacobian. I'm remembering it now. Well, maybe Sylvain remembers, or anyway, we can get back to what exactly it means. I guess it doesn't really matter. So generically, we can do this to the wandering points and to points on stable manifolds. So that means that since we have a generic diffeomorphism, if Fg equals Gf, there's an open and dense subset, and each consisting of the non-wandering points and the components in the interior of the non-wandering set, so that each component of this open dense set, we have G is some power of F. If we knew that the LIs are bounded, it's not hard to show, well, that you could continuously extend this Li to the whole manifold, and so it would have to be constant. So we have to do something else to ensure that these LIs all have to be the same, or all have to be bounded. So this is another type of perturbation. And this perturbation, you can't do a bare argument for. It's a much more delicate perturbation. It's a C1 small perturbation. And we show that for every x somewhere in the orbit, so there exists a k, so that if I look at the derivative of, and let's say for every, let me see if I get the quantifiers right here. Okay, so for every, oh, too far. So for every x, and for every large number n, there exists some k, such that if I look at the derivative of f, and exists an L, sorry. Oh, that's a way to erase, I suppose. For every, yes. For every m, there exists a case such that if I take the derivative of f to the m at f to the k of x, that this is large. So it's a perturbation on orbits. If I tried to do this perturbation on every point, I'd be screwed. But I can perturb every orbit. We can perturb every orbit in a C1 small way to make the derivative large. So this requires something that we call, maybe I won't get into the details. Anyway, if you can do this, then you know that on the other hand, if df, suppose Li is unbounded. Suppose Li is unbounded and it goes to infinity. Well then, on the one hand, df to the Li on the orbit has to go to infinity. But on the other hand, df to the Li is equal to dg. And dg, well, it's just diffeomorphism. So this norm is bounded. Contradiction. Okay, so the derivative blowing up implies that these Li have to be bounded. Okay, so that's sort of the whole proof, except there's one more issue, which I've now totally, there's no, as far as I can tell, that you can't erase. Unless someone knows more about Keynote than I do. I don't know how to erase all these comments and you can't see what I wrote. So, but I can tell you what's going on. So I told you the first property is generic. So this property that there's an open dense set, open dense set in M, so that if G commutes with F, then on each component in that open set, it's some power of G. That's generic. This property is only dense. So we get a dense subset of diff 1M has trivial centralizer, and we're like, well, that kind of sucks, you know. And here's the thing, when you try to prove that things are, I better finish up pretty quickly, but when you try to prove that things are generic, I mean, one thing that's often works, like it works with the Kupka-Smale property, is you show that the property that you want to be true, you show that that property is itself a G delta. So if your property is a G delta and you've shown it's dense, you're done. But guess what? The property of having trivial centralizer does not appear to be a G delta. I think it's not a G delta. In fact, I think it's not even Borel. Okay, so if you look in other contexts, like the measurable context, it's not a G delta. So how do we do this? Well, I don't remember whether, I can tell you it wasn't me, but I don't remember whether it was Sylvain or Christian came up with this trick of considering the Lipschitz centralizer. So instead of looking at the centralizer of F inside of diff, we look at the centralizer of F inside of the Lipschitz functions, and then Lippiomorphisms. And then everything just like works out magically because this is closed, basically because this is closed in the C0 topology. And so you can use the semi-continuity argument to get that the Lipschitz centralizer, well, I actually forget the details of this, but it's pretty cool. Maybe Christian can explain the rest of it at the end. But yeah, yeah, there's a really cool argument, but I forget how it goes. Okay, and so that's how you finish the proof. Okay, so I just want to make a couple remarks. You can ask the same question about vector fields. And in fact, Christian has proved some very interesting thing about commuting vector fields. And of course, you can ask the question, well, does the generic vector field have trivial centralizer? And there's quite a bit of work on this question, but this question remains open as well. So you can ask, so what do I mean? Trivial vector field, you know, X has trivial vector field centralizer. If whenever I take another vector field, then that commutes with it, then it has to be some constant multiple of X. Okay. So there's been quite a bit of work on it, and it's not known whether in general this is true, the generic vector field. But, and I believe these guys are here, so I'm happy to just give a little plug for this result. So Obata, Legui, and Santiago proved that if you take a C1 generic vector field and you have another vector field that centralizes it, then it's almost that one is a constant multiple of the other. So basically, one is a multiple of the other by some. Oh, okay. One is a constant multiple, is a multiple of the other by a function, by a smooth function. So it's interesting that knowing this, even generically, you can't go to this. And maybe Davi or Martin or Bruno would like to say something after I'm done. And more recently, Davi showed that, and he showed something a little more generally, but and this is kind of the question, this is kind of the, in some sense, the real question. Like you're given a vector field, you want to know whether the flow it generates has symmetries. Well, this is only looking at symmetries that come from vector fields, but what about symmetries from diffeomorphisms? So a diffeomorphism that commutes with the flow, is that always going to be inside the flow or be a time reparameterization? And on the surface, and this is actually trivial in diff1M, Davi Obata recently showed this on surfaces C1 generically. And I'll just give a sample of some further questions. The set of pairs of F and G, the commute is closed. So this is a question we asked in the paper. And to my knowledge, it hasn't been addressed or answered. It's probably really hard. What is the local topology of this set? Is it, for example, locally connected? So I know I should say there has been work on this question, but like on the circle in dimension 1, I guess. And Christian maybe can say something about it. I love just like tossing off these questions to more expert people. Here's another question. Is there even a single diffeomorphism that has no relations with other diffeos? Is there some F so that if I take any other diffeomorphism that's not a power, then it generates a free group with F? Again, I don't know of such an example. And consider this ugly set of, I just told you, is not a G delta. So consider the set of F with trivial centralizer. What is the interior of the set? Is there an interior, and is it a Borel set? And I think this kind of answer, the stuff, work of like, I'm not stating the original person, but Matt Foreman has told me quite a bit about answers to questions like this, where you're looking at like measure preserving systems. And this set is typically not a Borel set. Okay, and so I'll just end on this. So I guess we met just a little bit more than 20 years ago when you were 40 and I was 32. So here's to 20 more years, Christian. Thank you.
Thank you, Amie.
So are there any questions or comments?
I have a question.
Yeah.
Amie, hi.
Hi.
Look, speaking of symmetries, let's stay in the C1 topology, okay?
Okay.
Take a diffeo and look at the set of invariant measure it has. And let's discard the trivial ones like periodic orbit. So the non-trivial measures. Is there a chance that this would be characterizes the diffeo, that no other diffeo may share the same measure with him? So for any measure, like the generic diffeo has his own invariant measures that he shares with nobody.
Right, so it's sort of like dual to the question of the CR.
Is this kind of distortion, absence of distortion can be used, or?
Can anyone think of a simple counterexample? I mean, you could take a uniquely ergodic rotation on the circle and they have the same invariant measure. So what kind of,
No.
What do you mean?
No, but if generic diffeomorphism have the same.
Oh, it's a generic question. I thought it was a question more along.
Even the centralizer would be wrong. You take
No, I understand. No, I understand. I was thinking of the
generic
Philip
diffeo of the circle is UV, and he has an invariant measure that is singular. Yeah, even in the case of the circle, in the case of the circle, it's obvious because the conjugacy to the rotation is the measure, right? So you determine diffeo by the measure. There is a correspondence, diffeo and measure. And
I mean, on the circle, the generic diffeo is more small. I mean, it's the periodic points that the invariant measures.
No, but I was talking about measures that are non-trivial, so we discard these more small. We are in a weird kind
in the circle.
No, but you wouldn't want to discard them.
So you want that no other rotation is smooth for this measure. You have your diffeomorphism, which is C1, and you have the conjugation to the rotation.
Yes.
You have the other rotations, and now you tell, yes, no other rotation in that group is C1. So there is something to prove, but it looks nice Nice question.
Yeah, it's not exactly a generic question though, because you're asking only about irrational rotation.
In this case, you have to fix, say, the rotation number and talk about generic within the set. No,
Right. Yeah. No. It's cool.
Circle, because the question is empty on the circle in the sense of you
Sure.
said generic maps have only Morse make, but in general, maybe the measures of a DFO are unique.
Mm-hmm. That's a good question. I don't know the answer.
Beautiful question.
My other question is, you talked about Koppel.
Mm-hmm.
So what is the result again? It's C2.
There is a open on dense subset.
It's open and dense.
In any CR topology, R larger than 2.
Yes.
So that for diffeomorphism on the circle, you have trivial centralizer. It is open on dense
subset. This uses the bounded distortion on R, right?
It does, because you can conclude when you have an interval where you have kind of source sink dynamics
My question
between.
Is,
if it's C2, yeah.
Okay, suppose you have now in the C2.
C1 plus alpha, maybe, or?
No, in C2, but suppose you accept the closing lemma, like we do have periodic points, hyperbolic with stable manifolds. Can one try to adapt the argument to show that centralizer are trivial? I understand there is a
dimension?
Dimension, right? Because, say for example, in dimension 3 or 2, the periodic points will have stable directions that are dimension 1.
Well, I mean, the big piece of the picture that's missing is this classification of the interior of the non-wandering set. I mean, so you have stable manifolds, but did you want to assume that they're dense or something, or?
No, okay.
I mean, you can play a lot of games with stable manifolds. Let me see.
Some place where your question, I don't know, maybe it's already solved, but take a north-south dynamics on the sphere, on C2, and ask if the centralizer is trivial or open on dense subset. Because here the dynamic go from one side to another side, so you look at the, I don't know if there is distortion, but something like that.
Exactly.
But it's known for axiom A. So that it's open and
that is the equivalent to Koppel, indeed.
What's equivalent to Koppel?
Koppel use that the centralizer close to a fixed point is known because you can linearize,
right.
And then
what I say is that in Koppel,
she used the rigidity.
She doesn't need a tool of perturbation. It comes kind of for free, right?
Well, you assume you have rational rotation number, but yeah, rational. It comes for free. Yeah. Well, have you ever looked at the papers of Paulus and Yokos, Bassam?
But this is for Anosov, right? For
yeah, or axiom A. But I mean, it does use in a very key way the dynamics. I mean, normal forms, the dynamics on the stable and unstable manifolds.
Yeah.
Yeah. I mean, you know what the local centralizers are. And then the point is like on an interval. And the point is you need them not to match up. Right? There's a Mather invariant that tells you whether you can glue them together. And if you can't, then the centralizer becomes discrete. And you can but what did you, I wanted to say what we proved with Gioia since it's related. So you asked, like Koppel showed, in fact, showed open and dense. And you might ask, is the same thing true in the C1 topology? And the answer is
No.
pretty easily no on the circle. And even, I guess, on any manifold, right? We constructed an open, I'm sorry, a dense, a locally dense, so an open set of diffeomorphisms, I guess, close to more smell or something like this,
Yes, we
where
made that on surfaces, yes.
we did just on surfaces, where non-trivial centralizer is dense.
Yeah.
We're just on surfaces. So it's very different in C1 than C2.
Palis and Yokos is a generic result for Morse-Mail and Anosov that they don't commute, they have a trivial centralizer. And you asked this question about, is there an open set of C1 diffeo that have trivial centralizer? All of them?
Yes.
There exist.
Does there exist an open set with trivial centralizers? So
Yeah.
we showed that in general it's not open,
Yeah.
but
There is an open set.
there is an open set.
I have a paper, a short
Who's
one
there?
with Leonard
Oh, who?
Packer. Where
Who's talking?
It's
Todd?
Yeah.
Oh, hi, Todd.
Yeah, no, there's a short paper I have with Leonard where we show an example of C1 open.
Ah, okay.
Yeah, so there is, I mean, it's just an example, but there is at least something in there.
What dimension?
I'd have to remember. I think 2, maybe on higher on tori, kind of taking hyperbolic toral and perturbing them.
Oh, yeah. No. I'm sorry. There exists. Sorry.
Yeah.
Yes, there do exist. And you showed C1 open as
Yeah.
opposed to, yeah. Yes. So the question is, in general, what is the interior? Do you
Yeah.
need some kind of hyperbolicity, for example, to get an to have that property be open?
Mhm.
So.
Okay, so are there any more questions?
Maybe I have a comment.
Go ahead.
I would like to thank every participant, every speaker, and the organizers for this nice birthday. So it was very nice for me, and thanks a lot.
It was, I think it was our pleasure, Christian. Well, I don't know if it was your pleasure, but it was certainly my pleasure. I enjoyed the talks and giving the talk as well. You've been, I should say, I mean, you've taught me so much over the years, Christian, and really shaped the kind of mathematician I am. There's just so many good things I could say about you, and as a mathematician and as a person. So, thank you.
Don't try to make me cry.
You're gonna make it.
Sure.
Quite nice, but not very nice, Christian. But we all hope that next year we will be all together in Dijon to celebrate your birthday presentially there without any pandemic or whatever. Huh?
Let's hope that.
Yeah, and to toast very good wine from Bourgogne.